it's about time. Let's talk about the topic that we are going to learn. We are going to discuss today, okay? So as you can see right here, today we are going to talk about the topic 3D rendering, okay? Rendering is pretty like the display or drawing, but specifically when we are talking about the rendering, it's more like the display for the 3D object, okay, 3D object. So you can see the subtitle right here. We are going to focus on the surface rendering. Okay, so surface rendering could help us to generate the model for the 3D printing. So we are going to learn this today. Today we are going to separate the content into two different parts. The very first part, I'm going to introduce what is the surface rendering. How can we generate the surface, or how can we model the surface of a 3D object? For the second part right here, you can see once we have the 3D surface, we can actually do something afterward. So this is so-called post-processing. After we create the model, we can still process something on it to improve the quality or to improve how it looks like. So we are going to talk about this in the second part. So again, if you didn't download all the handout and materials for today's lecture, please do it now. You can visit my website to find everything you need. So let's start from the very first part. What is the surface rendering? Okay. So now, as you can see right here, 3D rendering is the way that we can display the object, the 3D object. And basically, there are two main types of the rendering. The very first one is the fallen rendering. As you can see right here, you can see the terminology, direct fallen rendering right here. Okay, this is the very first way. And there is another way, surface rendering. This is another way. But I have to say, for this semester, we are going to focus on the surface rendering because this one is good enough. This one is sufficient for all of us to do this 3D printing. But it is still my responsibility to introduce what is the direct fallen rendering to all of you, okay? Let's just take a look on this video clip. This one. So I just want to let you know that this 3D object is actually reconstructed from the CT images, okay? CT imaging, computed tomography. Okay, let's just take a look on this. So now you can see it's more like a model of the hand, right? However, we see in this hand model, you can see, for example, this is the bone, okay? And now you can see here are some muscle, then come back to the skin level. So basically, it is reconstructed using the slice by slice medical images. And you can find out, you can switch from different angle, and the different tissues right here can be actually displayed using different color. Okay, based on the property of this tissue. So you can see the short description right here by selecting color, opacity, as well as the shading. I think shading is something that we can actually see the 3D object. We need to see the shadow. This is kind of the way that we can display a 3D object right here. So anyway, if you can display the object, pretty like what we displayed in this short video clip right here, using different color based on the tissue property right here, then the method is so-called direct fallen rendering. However, you may find out this kind of the direct fallen rendering is kind of the complex technique. And for 3D printing, we don't really need this kind of the complicated model right here. So you can see the right-hand side. Of course, you can display the hand or the skin using this kind of a color, right? And you can also display the bone, the skeleton with, I think, partly the muscle and as well as the vessels right here. You can display all of the tissue using different color, right? However, for the 3D printing, we don't need to do this because it is just too complex, and we don't need to switch color that much when we are printing something right here. So today, we are going to focus on another way for the 3D rendering. This is so-called surface rendering. So again, let's take a look on the example in the lower part right here. You can see for the left-hand side, it is actually the dental CT. I mean the computed tomography for the teeth right here. Okay. So what we can do, I think we all learned what is the ROI poly before the midterm computer test, right? We also learned what is the stress holding. Basically, we can pick a certain value as the cutoff point, and then we can determine which part of the tissue that we'd like to keep or focus on. Okay, so you can see this kind of the CT imaging is actually processed using the ROI poly and the thresholding approach. So now we can focus on the actually the teeth and also the TMJ. I think that is kind of a joint on your face, I have to say. Anyway, so you can see right here. So for these red areas, these areas are the target that we'd like to reconstruct the 3D model for it. So now you can see for the right-hand side, this is the reconstructed surface model. So now you can see what is the difference between surface model and follow rendering. Follow rendering, we actually care about the content within this object. But for surface rendering, we only care about, you can say, superficial surface. We only care about how it looks like, what is the appearance right here. So you can take a look right here. Actually, the right-hand side is the surface rendering of this kind of the target area that we labeled in red in the left-hand side, okay? You can find out it's actually good enough. It's actually good enough. It's actually tell us what is the appearance for this kind of the 3D structures right here. So basically, what is the surface rendering? It's simply like the binary technique. Binary means two values, either to be 1 for your target area or either to be 0 for the background area. So this is so-called binary rendering. You can see right here why we can simply display the area using red, because this is the target area that we'd like to reconstruct the surface model. But for other regions, for example, the muscle or even the spinal column right here, it's only the grayscale image right here. That means they are the irrelevant area or they are the background, okay? So this is something we call the binary, 1 or 0, binary rendering technique right here, okay? And in MATLAB, we can actually reconstruct this kind of the surface pretty easily. There is a very good built-in function named as the ISO surface. You can see the red labeling right here, this one, ISO surface. So you can easily use this function to reconstruct the surface from the medical images. This is something you will learn later, okay? Okay, so let's take a look right here. I try to enlarge a very small part of the medical image right here. Now think about this. Every single medical imaging is actually constructed by a matrix. For example, 256 by 256 or something. But right here, I zoom into a very, very small area. You can see right here, it's more like 7 by 7 matrix right here. Okay? And now you can see, of course, each pixel or each element of this matrix definitely come with different intensity. That means different value, right? And what you learned in the last week, you know that we can color or we can give specific grayscale for each pixel based on the intensity. So you can see right here, for the right area right here, it's more like, the pixels or the elements with higher value. So you can say maybe right here, it's more like the 300 or above. The value is more like 300 or above. And for here, you can see the black or dark area right here definitely has lower values right here. So it's more like 50, maybe 20, or maybe close to 0. So you can think about this, okay? But if we'd like to create the surface model, what do we need to do? We need to do the stress holding, or again, the binary technique right here. We need to determine where is the area that I'd like to keep and where is the area for the background. So you need to determine a cutoff value right here. So for example, if you are using if you are using a higher threshold, for example, 250. If you use the 250 as the threshold, you may find out this kind of the boundary or border. What does that mean? Actually, this red line right here is the border between the pixels. And for the right upper corner right here, these are the pixels, or these are the elements, always the value larger than 250. Okay, so right here, this is the target area. And for other area, like the left and the lower corner right here, these are the background because they all have the values lower than 250, right? This is the case, okay? Now think about this. If you pick a lower threshold right now, for example, now we change the threshold value from the 250 to like, 50. How about this? You may find out now this surface boundary would move from this way, this part to this part, because now lots of the pixels actually have the value larger than 50. So now you can think about this. The selected threshold value would control the surface boundary or surface area, okay? But now think about this. If we really use this red boundary as a surface, it may be a tragedy because it may look very ugly because it is more like a, I don't know, the irregular boundary or something. Every single time when we try to create a surface, we like a smooth surface. So everything will look pretty, right? So what you can do these kind of things. The blue line right here represents the reconstructed iso surface. So we really want the surface to be smooth, to be pretty, right? So you can see it's basically like the curve goes through all the corners of the red boundary right here. So this is a beautiful appearance right here. So now for this case, you can also see these kind of things. Okay, so basically for this slide, you should understand what is the relationship between the selected threshold value and the reconstructed surface. Okay, think about this. And another thing you should learn is that for a very complex surface, we can actually reconstruct this surface using the polygon. The polygon. What is a polygon? For example, a triangle itself is kind of the polygon, right? You can, of course, using the rectangular, maybe the rectangular shape or maybe the triangular shape would be a good idea. But I have to say, triangles are the common way that we try to reconstruct the complex surface. So for example, right here, you can see this is the model that I just displayed for you. You can see the teeth right here. You can see the jaw right here. Okay, you can see a lot of the bone. But actually, this kind of the bone can be reconstructed using multiple triangles or multiple triangular surfaces right here. Okay, so you can see every single part right here is triangle, right? You can see. However, the shape of the triangle, the area of the triangle are very different. Okay, so this is another example right here. So basically now you can understand a smooth surface can actually be represented using this kind of idea, polygons, specifically triangles right here. So now you can see, let's define some terminology right here. For any single triangle right here, we can define face. Okay, so triangle, the surface of the triangle is called face right here. And again, you can define edge. Okay, so for a triangle, you will have 3 edges, right? So you can see the red lines right here. These are the edges of the triangle. And finally, for each triangle, you will also have 3 vertices, right? So you can see the blue points right here. You have one vertex, second vertex, and the final vertex right here. Okay, so think about this. So now you may understand that this kind of the complex surface can be represented using lots of the faces, lots of the vertices right here. Okay, basically there are lots of the triangles right here. Okay, how to actually find out these triangles? There's a very, very good algorithm called marching cube. You can see the right words right here, marching cube algorithm. So it will help you to cut down this kind of the complex surface into small pieces. And you only need to think about how to reconstruct the faces for this small cube. So this is so-called a marching cube. So marching cube means you're continuously moving the cube. You are scanning this kind of a surface using a cube, but you are continuously moving the cube. Go through the following or go through all the surfaces to reconstruct this kind of a triangular face. Okay? So you can see this is the idea. But before I go into the detail, I want to just take a look right here. Again, this is just simply a video clip, but it can help you to understand how to reconstruct the surface using the marching cube idea. So take a look right here. For example, for this kind of the image imbalance right here, only 3 points, you can see only 3 points or only 3 pixels would be the target areas. Okay, so basically I'm going to reconstruct the surface to actually contain these 3 target pixels right here. So what should it look like? You can now take a look right here. The marching cube means I'm going to deal cube by cube, only one cube at the same time. You can go through the whole volume, but every single time when you scan to a specific cube, you will consider how to reconstruct a specific face or triangle right here. So this is the case. It's pretty quick. I think it's a very, very short video right here. But now you can see if we'd like to represent this kind of a surface, you can see this is the example. For 3 points, you can reconstruct the surface like this one. But for each cube, what just happened in the video? Now you can think about this. For each cube, you should have eight vertices, right? Or maybe you can think about 8 pixels right here. And now there are actually several different possibilities right here. For example, if you are dealing with this kind of cube, for this left and this one, okay, let me use the pointer. Yeah, this one. If I dealing with this kind of a cube, now you can see there is no highlighted pixels right here. That means there's no target area within this cube. So you don't actually need to reconstruct any surface or any face for this situation, right? So let's go for another one. If this is the second example right here, for 8 vertices or for 8 pixels right here, only one is the target area. What would happen? You will build this kind of a triangle, actually cover this corner. Okay, so this is the second possibility. And there is a third possibility that actually 2 of the 8 vertices right here belongs to the target area. And now it's pretty like you are creating a tent, You are trying to cover these 2 pixels right here using, again, 2 triangles right here. So you can see lots of different examples. If now the pixel are not the neighboring pixels right here, now you need to create 2 separated triangle to cover these 2 target pixels right here. So there are lots of different examples when the target pixels actually increased within this cube. You can see there are lots of different possibilities right here. However, there are only limited cases within this cube because you can try to count. You only have 8 vertices. So there are limited conditions that you are facing right now. So if you can define for this limited condition, you can always have the solution. So what you need to do is you just try to move the scanning cube through all the volumes. Then you can do exactly what you see in the video. So let us take a look on the video again. So now think about this. When you are going to each cube, for example, the very first cube, you only have one pixel within the target area, right? So all you need to do is build up a triangle to cover it. Okay, so think about this. go for the first one, just one single triangle. But for the second one, you need two triangles to cover these two pixels or two vertices right here. So if you can go through all the followings, you can actually create the surface for this kind of situation, okay? So for the real case, of course, the target pixels would be much more than these three points, right? 3 pixels right here. So you can actually build up a very, very huge surface model right here. Okay, so what you are going to learn for the very first part, you need to learn how to use this function, iso surface. Again, you should help this function later, but I just try to give you a quick hint right here. What you can do, of course, the function name is iso surface, all in lowercase, okay? And then you can give two inputs. The very first input, V right here, represent the imaging. Of course, it should be an imaging with 3 dimensions. For example, 200 by 200 by 100. Okay, it should be a 3D images, right? It should not be a 2D imaging. If your V only has the size like the 200 by 200, it won't work. Okay, it won't work. You should give a 3-dimensional image volume right here. And for the second input is so-called ISO value. That is the threshold value. Okay, think about this. We have already discussed about this. If you are using a higher threshold or higher ISO value right here, you will get a small surface, right? Because only limited pixels may have the value larger than this ISO value or the threshold right here. So what you can do, of course, you can just try different value for this second input. But for lots of the condition, normally we have already prepared our imaging to let all the image values be 0 or 1. 1 represents the target area, 0 represents the background. Then normally you can also skip. You can also omit. That means you don't need to input the second value because normally it will automatically set the boundary between 0 and 1 as the ISO value. That is what you can see. And what are the outputs right here? You can see the outputs. We do have F and V, right? But please do not be confused because this V is different from the input V. The input V is the image volume. But what is the output V? This output V are the vertices. As we mentioned before, that for this kind of a triangular surface, we can have the faces, lot of the face, right? We can also have the vertices. So you will get face, you will get vertex right here, okay? So now, what I'm going to ask you to do right now, again, please create a new script file. And I need you simply put all the 3 command lines right here into the created script file. Okay, just try it now. And you should take a look on what is the F, what is the V. I mean the output F and output V. So first of all, you can take a look right here. For the very first line, I try to create a 0 column with a size like the 10 by 10 by 10. So it's a fallen matrix right here, but only has a 0 inside, right? But for the second line right here, for the second line, you can see I try to set a part of the region, the value of a part of the region to be 1. So you can see for the second to ninth row, second to the ninth column, second to the ninth slices, the value would be changed to 1. Okay, you can see right here. So now you can maybe imagine what is the shape of this kind of the fallen. In the surrounding area, I mean the first row, 10th row, first column, 10th column, first slice and 10th slice, they all have the value of 0, right? But the central part of this A matrix would have the value of 1. So now 1 is the target area. 0 is a background. So what you can do, you can use the ISO surface to reconstruct this fallen, okay? So just do it down and tell me what you can see for the F and V, okay? So I'm doing the same thing with you right now. Of course, you can just close O. Okay, then you can start by creating these A's. I do want this to have this three-dimensional column. And I'm going to set everything in the center to be 1, right? And finally, I'm using the isocolumn to help me to reconstruct the isosurface, right? Isosurface right here. Okay, we need to use the A as the input and the 0 as the ISO value, because now I know for A it's mostly 0 and 1. I can use the 0 as the threshold. Okay, so I think you have already finished it. You can simply give it a name. Okay, and run it. So first of all, you can just double click on the A. Okay, let me help you. Double click on the A. Just take a look. What do you have within the A? For the very first slice, of course, all in 0, right? But now start for the second slice. You can see this is the second slice. Actually, you can see the first row or first column are zeros, right? Even the final rows are all zeros, right? Of course, for the final column, it should be all zeros, right? So anyway, I think you can just imagine what is the shape of this kind of the matrix of A, okay? And now we use this isosurface to reconstruct the surface, right? You can see a lot of the face, a lot of the vertex right here. So basically, you should be able to see 764F and 384V right here. Of course, this is for vertices right here. So what is the content of these two variables, F and V? Let me take this example for you. So think about this again. Let's start from just one of the face. For example, now you can see on the screen, this is face number 1, just one of the example, okay? Again, I mentioned for the face right here, each face, each triangular face definitely can be reconstructed by or represented by 3 vertices right here, okay? So one face, you can see V1, V2, and V3. Again, V represent the vertex, okay? So you can see for this face, this is the face number 1, and you may find out for this F variable, we do have 3 columns right here. What does that mean? That means for this face, it actually contains the vertex number 1, vertex number 2, and the vertex number 3. Just what you can see right here, okay? But the most important thing is that what is the coordinate for each vertex? Because you want to plot this face in a 3D space, right? So you need to know the coordinates of all the vertices right here. So basically, for this face, you do have vertex number 1, 2, 3, right? You can see this face is constructed by vertex 1, vertex 2, and vertex 3. So what is the coordinate for V1? So let me put this in this way. Okay, this is V1. This is V2 because you see the 2, right? This is V3. And the most important, what is the coordinate? It's actually recorded right here. This is a V1. This is a V2. This is a V3. So this is X, Y, Z. You can think about this. So this is kind of the table that can help you to define where is the location of this face, because each face is reconstructed by 3 vertices. And now you do have the coordinates for each vertex. V1, it is actually located at X4, Y10, and Z2, right? So this is the 3 coordinates for each vertex right here. So let's come back to take a look right here. So for the example that I just displayed for you, this A actually can be reconstructed using how many faces? Take a look. Actually, 764 faces right here, right? And again, each face would be represented by 3 vertices right here. So you can see 3 columns right here. But the most important thing right here is for each vertex, you need to define the coordinates right here. So now you can see V right here, you actually have 384 vertices. Okay, so you may ask a question, why? I have 764 faces, but I only have 384 vertices. It doesn't make sense because teacher, you just mentioned that for each face, you need 3 vertices. Then supposedly I should have the vertices number like 3 times of the number of the face, right? But the truth would be 2 faces can share same group of the vertices. For example, these 2 faces, you can see face number 1 and face number 2, they can share 2 vertices, right? So you can see actually V2 and V3 can belong to face 1, but it can also belong to face 2. So I have to say, if you are dealing with the continuous face, the vertices should be shared by multiple faces. So actually, this is so-called continual face. It is not the broken face, right? So now you can take a look right here. For these 2 faces situation, now you can see, okay, for F1, face number 1, it is actually, sorry, right here. This is for face 1, right? This is for face 2, face number 2. So now you can see 2 and 3 are the shared vertices for both faces, right? They both have vertex number 2 and vertex number 3, right? But now, because the second face actually has another point called V4, so now you need to define where is the location of the V4. So based on this idea, now you can think about, I can actually just make the list longer to represent the complete surface. Okay, so now you can think about, if I do have huge number of the faces, that means it may be a very huge surface or complicated surface right here. Okay, so I think this is what you can understand right here. And what is the next step? Okay, now we do have the face. Now we do know the locations of the vertices, but how can we display it? So let's come back to this kind of the graphics structure that we mentioned in the last week. Now take a look right here. We do have another spatial object called patches. We introduced what is images, what is line, right? But today we are talking about patches. So now you can think about patch means a small surface. So patches means we try to display a lot of small faces right here. So that is what we are going to do. Again, if you would like to display this kind of a page object, you can only define it under the axis. Okay, so you can see the root is your desktop. You can create a new figure, create a new axis under it, and then you can display the patches within this axis. So now this axis can be 3-dimensional. What we learned in the last week, mostly only 2-dimensional, right? However, MATLAB can easily extend this 2-dimensional axis to be 3-dimensional one. So not only X and Y, which means rows and columns, you can also have the third direction like Z or slice direction, okay? Okay, so patch is also another function that we can use in the MATLAB. So what you should do right here, you can see the usage of patch is pretty easy. Patch, of course, the function name. Then you can use this kind of the pair input of the variable. This is the first pair. This is the second pair. Okay? So what is F and what is V? You just got it, right? You use the isosurface, and the isosurface function gives you 2 output, F and V. So basically, you can simply use the patch function to display all the V and all the vertices right here. Okay, so what I'm going to ask you to do right now, just add 2 more lines right here. Just add these 2 more lines right here. And tell me what you can see. I think what you can see is on the right-hand side. you should be able to see this, okay? Just add these 2 more lines into your script. Again, I'm going to do the same thing with you. Figure and a patch, right? Figure and a patch. I'm going to do the same thing. Figure, patch. Again, you need to remember that a patch should be inputted with the pair variables right here. First one is faces. F. The second one is the vertices. So you can see we always use the plural. However, the upper or lowercase of the variable name is not that important. So you can simply put everything in lower cases right here. However, the variable name f and v is actually case sensitive. So you should to make the right input right here. Okay, so once you finished, all you need to do is again save it and run it again. So take a look what would happen. Now you will see something like this one. You will say, no, teacher, it doesn't look like what you displayed in the slide, right? All black. However, I can see 4 corners right here, like the red triangle right here. Now, what you can do right here, just take a look. You can see there is a toolbar right here. And for the third option right here, you can see the notation is rotate 3D. Okay, click on it first. Then you can just left click on your mouse and drag it. Okay, just do it by yourself. And tell me, what is this? Think about this. What is this? It looks like a cube, somehow a little bit weird, but it may be a cube anyway. You need to continuously imagine what is the shape of the A, because this is the isosurface of this A variable, right? So think about this, okay? Again, I totally agree that this is a pretty ugly display for this surface. Pretty bad because all black. All black means I cannot see anything, okay? What we can do for the next part, because we know this is not good enough, but what happened? I have to say, why this cube is displayed all in black? Because the answer is pretty simple. We don't have the light. Think about this. If you put something with a whole dark environment, no light right there, you cannot see the appearance of it, right? So what we should do right now, we should give the light. We should give the light. Okay, so what you can do right here, you can see, I'd like you to modify the final line. For the final line right here, it simply has the input of F and V, right? But now I'm asking you to modify this line. I just want you to give one more input right here. You can see the face color. You can guess what is the face color. What is the face color? I think it's pretty easy, right? The color of all the triangular face right here. So now you can see 0, 1, 0. What does that mean? What does that mean? Think about this. We know this 1 by 3 array actually follows the rule of the RGB color coding, right? So for 0 means no component of red, no component of the blue, but we do have 1 for green. So basically 0, 1, 0 is the color code for the green, okay? And then another thing that you should do is you should add 3 more lines into your script. You can see the lightning. You can see the camera light. You can see the axis equal. Okay, so do it now. After you key in all the commands, again, run it again, you may find out something's changed. So let me do this with you. I think I can directly copy all the command lines into my script. Okay, you can run it again. Again, I think initially you can only see the top of the cube. But again, what you can do, you can rotate it by clicking this button, rotate 3D button, right? Then you can just rotate it. Okay, so let me take the control back. So after you put all the things into the script, you should be able to see something like this one. Okay, so now it is really like a cube, right? It is really like, so now you can think about this, why the corner looks like this one. Because the Martian cube algorithm tells you if you only have a single pixel or single corner, it will be covered by a, oblique triangular surface right here. Okay. I think this cube is pretty cute. Okay, the cube is cute anyway. So now you can try something. For example, can I change the face color? For example, I want the red one. I don't like the green one. You can do this. I simply change the color code right here to 100. You can run it again. Now you would see the red one, right? Because we have already learned it. You can change the face color. Okay. So here is something that you should know. And what is the function of the 11s and 12s command lines right here? This is the definition, or this is a declaration of the light. So the very first one is the type of the light. This go round is one of the type. You can simply help lighting. You may see this function actually offers you a lot of different choices. So this one, okay. You can see the flat type, you can see the go round type, and you can see none. That means turn off lightning. Okay. So basically, I like to use this one, but feel free to switch the type to the flat. Okay. So basically, you can use flat, something like this one. I think it's pretty okay. Okay. And what is this one? This is the position. This is the position of your camera light. Okay. So basically, you can determine where's the location of the light. And why this actually defined by two input values? Again, you should help camera light, right? You can help it. And now you can see to define it, you need to use two angles for this, AZ and EL. Okay, this is the angle for the 3D objects that you can define. So you can change the value. Normally, you should change the value between negative 180 and positive 180 because this is the degree. Okay. So you can just simply try it. And every single time, just take a look on this corner. On this corner, every single time when you are rotating your cube, you will see two values right here. That is the angles. So you can see AZ and EL, right? So it can help you to understand what is the value of these two angles. It can define the view angle, okay? So you can see the two values right here. I cannot just leave my mouse right here because every single time I release the left button, the values would vanish, okay? But anyway, you can just try it by yourself, okay? Okay, I think this is good enough. So I'm going to give you a real example. I mean, the medical imaging example right here. So now you can take a look. I'd like to take this L spine. L means lumbar, okay? Lumbar spine, CT as the example. So this is just I think it's just 8 slices of the CT imaging for one of the lumbar spine, okay? So the goal right here is that we'd like to reconstruct this spinal column, okay? This spinal column, this bone, into a 3D model right here, okay? So you can see left-hand side is the original CT slice, but the right-hand side is the model that we'd like to create. So what I can do right now, I think you don't have time to key in everything by yourself, but what I can do, please just open one of the M file, one of the script that are provided to you in today's folder, MI materials underline L12. You can find this L spine model.m file. Okay, you can simply just open it. And what I can do right here, you can run it. Okay, just run it. And I will explain all the details later. But what you can do right now, just open the code, L spine model. Okay, just run it. Okay. It may take, I think, several minutes, depends on the performance of your computer. But anyway, once it is done, you should be able to see this 3D surface of this spinal column. Again, you can rotate it. You can rotate it. But of course, if your computer only have very limited performance, then you may need to wait for a little bit longer. Anyway, so if you can see these 3D objects, just raise your hand. Just 2, 3, 4, 5, 6, 7. Don't be shy to raise your hand. Okay, good. So let me take you to go through the command lines, and you should make sure that you fully understand the meaning behind all of this, okay? So now think about this. For the very first part, you can see clear close all. I don't need to explain this. But for the first command line right here, now you can see load. I load the data of this one, else by underlying data, okay? So I have to say, this kind of the model will be pretty similar to what you have for the final project. So you should try it again. Let me just simply run this part again. Once you load this kind of the else by underlying data.met file, you can see it should be somewhere right here. Yeah. Data, yeah, this one. I provide this within the subfolder data right here. Okay, so for your final project, you can also download pretty similar met file from my website, right? Do remember, you can simply use the load function to get the content, okay? And the content would be pretty similar to these two variables right here. The very first variable, you can see img. This is the image file, right? This is the image file. So you can see the size, 512 by 512 by 8. Because we only focus on a specific spinal column, so we only have 8 slices right here, okay? But another important thing is the image resolution. You can see IMGRES. What is the image resolution? You can think about this, it's more like the pixel or voxel size. So the unit would be millimeter. So 0.31 millimeter by 0.31 millimeter. But now you can see for the slice direction, actually the slice thickness is 3.75 millimeter. So compared to the pixel size, the slice thickness is actually pretty huge, right? So let me plot it on the PowerPoint. So now you can think about this. For any pixels, sometimes we say voxels. Within the image matrix, the size right here is pretty like this one. That means for the row and the column, you just see the size is pretty like the 0.3 something, right? But for slice thickness, this is also 0.3. But for slice thickness, it's more like 3.75. So actually, compared to the row and the column, slice thickness is pretty huge, right? It is actually pretty huge. You need to make sure that you're fully aware of this kind of a difference right here. Otherwise, you may create this kind of the image. Pretty like a flat, a flat model right here, because you ignored the issue of the difference between the slice thickness and the implant pixel size. Okay, you need to make sure you know this. So let's come back. Let's go back to this part. Okay. So now, for the second part right here, I think this part is only for the image display. And this is a reason that why you can see this image, okay? So simply, I just display the third slice of this image file. We do have the 8 slices inside, right? I only display the third slice with this specific image contrast right here. Anyway. And then, for the next part, you can see I use the ISO surface. And right now, you can take a look right here. You need to make sure you input the correct ISO value. But you may ask me, how do I know what is the good ISO value? I need to tell you what you can do right here is this one. Right here, what you can do, you can again use the function of the second icon right here. This is so-called data tip. Click on it, and then your cursor will become a crosshair, right? What you can do, you can click on anywhere you'd like to see the value. Now you can see the muscle. Right here, this is actually the muscle, the psoas muscle. You can see the intensity is around 38. But now you'd like to reconstruct the bone, right? The spinal column, right? So you need to find out what is the optimal threshold. So take a look right here. For the bone, you can see the value can be as high as the 524, right? So now you can think about what is the optimal threshold. For the background, it's more like, 20, 30, 50, or even for this kind of area, it's more like negative values right here. So if you really want to separate the spinal column from the surrounding muscles right here, I think you need to pick a value around maybe 50 or to 100. But in this script, you can see I picked the value like the 100. Of course, you can try it. You can change the value and try it. Try to find out which ISO value is the best choice. You can do it by yourself. So again, I just want to emphasize that MATLAB itself is more like an experiment. You can just change the value and to see whether the result is good enough or not. And now you can see the following area is pretty similar, right? The only thing is that I changed the face color because this one looks like a bone, okay? And you can see not only the face color, I only changed the edge color. You can see I put none right here because I don't want to see the grid. What is the grid? For this example, you can see lots of the black lines right here. This is the edges of the triangular face, right? When I am displaying something for real, I don't want to see these kind of lines because it makes everything like a fake thing, okay? So I can actually hide this kind of the edge line by setting the edge color to be none, okay? That means no color, no display of the edges. And I think for the line 18 and the 19, you should be able to understand this. But now you can see for the line 20, I did put another function right here. What is view? You can see, again, these are the two angles right here. So what we did before is that we manually rotate the 3D object, right? But actually, you can use this code to let MATLAB to change the angle. So you can take a look right here. I input the value like the negative 155 and a 50 degree right here. So take a look, again, take a look right here. So you can see the value is initially set to this negative 155 and 50, right? Just take a look. I cannot move my cursor right now. But just take a look. It's pretty close to the negative 150 and 50, right? So this is the way that if you don't want to manually rotate your model, you just want the display can automatically change to the best or optimal angle, view angle by itself, then you can use the view function right here. All you need to do is to input the two angles that you'd like to display. Again, you may ask how to determine this. Of course, just by test. You need to rotate it by yourself first, but you can just find out the optimal view angle right here. Then you can put it in as the two inputs for the view function right here, okay? So the only thing that I, skipped is the code number 12 right here. Let me do something. If I just hide this line, I put the percentage mark right here, right? I hide this line. Let me show you what would happen. Let me show you. I run the section again, but now I hide the line 12 in purpose. So let me take a look. Just wait. Now you can see the results. Oh no. I need to do everything again because I have already modified. Okay, let me do it again. Just wait a couple seconds. Now I can see the results right here. Again, let me rotate it. You may find out something weird, right? Compared to the previous result, you may see, wow, what's going on with my model? It's just like a thin plate, right? I cannot actually see the real volume of the spinal column. Why? Because for this kind of case, we ignored the issue that I just mentioned, the difference between the pixel size and the slice thickness, right? So take a look for this example. Actually, most of the medical image data set would be so-called anisotropic. In Chinese, anisotropic means 非等向, or basically it is not a cube. 不是立方体. You can think about this for every single voxel. In this example, you have the implant pixel size like 1 millimeter by 1 millimeter. But for slice thickness right here, you actually have 2 millimeter slice thickness. So it may cause the problem because this is not displayed in the equal dimension, right? So you will get a result that you only have 8 slices. 8 slices for the z direction, right? But you have 512 pixels in row and column direction, right? So it will cause the result to be this kind of weird because you only have 8 slices right here. So you can see it's pretty small. You can see the number right here. The maximum value is 8. And this is a reason because you didn't correct the difference between slice thickness and the implant pixel size. So I created a function called isotropic volume. It can help you to transfer this kind of the anisotropic volume into isotropic one. Again, isotropic means every single voxel is a cube. So you can see 1 by 1 by 1. 立方体, right? It's a cube. So take a look for the command line 12 right here. Let's take a look right here. What you need to do, and I promise you that all of you definitely need to use this function for your final project, okay? Because for most of the medical imaging, you don't have the isotropic volume. So you need to correct this issue by using this function, okay? Again, you need to input this original imaging, and then you need to input the imaging resolution. So basically, I have already provided you the image resolution, right? 0.31, 0.31, 3.75. All you need to do, you just put each of them as the second input, third input, and the fourth input. Okay. And this is kind of the property that you can control your result, but you don't need to change it. Okay, so right now you can find out if I go through this, take a look. This is the original image size, right? 512 by 512 by 8, right? If I use this function, what would happen? You can see the result would become 513 by 513 by 85. I actually increase the number of the slice because you need to correct this issue, right? I have to say for each slice, it can actually create 10 more slices because the implant resolution is more like 0.3, right? But slice thickness is 3.7. So they are 10 times difference. So you can see I actually increase the slice size by 10, around 10, I have to say. Okay, so this is the way that if you do have these kind of things on hand, then you can actually create a right model with the actual column size right here. Okay, so let us take a look for the final result right here. This is the situation that you actually expand the 8 slices into 85 slices. Then everything looks real or normal, I have to say. Anyway. So this is something for the command line 12 that you should learn. So I'm going to give you 2 more minutes. You can just take a look on this L-spine example. Just please make sure that you really understand each command line right here, okay? Just read through all of them. You can feel free, you can just discuss with your group members. And if you want, you can download. You can download the file for your own project. You can try to use the load function to read it into the Manable workspace and try to take a look on the, for each topic, you will have the image and the image resolution. Just take a look on it, okay? You can do it now. So you will have 2 minutes to have the discussion.